All right, hello. My name is Bailey Carruthers,
And I'm Chris Miller.
and this is our blockchain exploration program project.
Suppose it's both.
Yeah, that's fair. All right, so just a quick overview of what a blockchain is. The basics: it is a type of database, and it essentially boils down to being a glorified linked list. Stores data in blocks that are chained together. Crazy, right? Blockchain. These blocks are stored in chronological order of when they are generated, and multiple types of data can be stored within these blocks. The most common, of course, being cryptocurrency. A couple other things about blockchains is that they are immutable, decentralized, and they are generally, in their most common forms, a public ledger. And like I said, most common data is transactions, so it would be fair to call them a public ledger of transactions. Proof of work. So, proof of work is what we ended up doing with our implementation. Proof of work is a decentralized consensus mechanism that requires members of a network to expend effort solving an arbitrary mathematical puzzle to prevent anybody from gaming the system. It is used for mining new tokens and validating transactions, and allows transactions to be processed peer to peer without needing a third party. Decentralized again. Um, Proof of work scales as more miners join the network. So the more nodes, the more people connected and actively participating in the network, the harder it becomes to find these new blocks. That way, the block time stays about the same. Proof of stake is the emerging alternative, but expanding upon that is outside the scope of this presentation. But is blockchain perfect? No. 51% attacks are a thing. Essentially, if you can control more than half of the hash power on the network, you can control the network. This goes back to being decentralized. Pros and cons. You're always going to have bad actors that want to steal your money, but there are ways that they handle it, such as branching and a couple other ways. But it is still a drawback. Some of the more notable ones, like on Ethereum right now, transaction fees, also known as gas, can become an issue when the network becomes congested and too many transactions are being queued for blocks. It can get overloaded and the gas fees will go up. Another thing is new technology can be hard to learn or understand. Some of the bigger parts are easier to talk about, but there's a lot of minute details that are a bit harder to understand and sometimes even harder to explain to somebody that has no idea what you are talking about. So blockchain versus cryptocurrency, a distinction that must be made because the two go hand in hand but are distinct. Blockchain, it is essentially a glorified linked list, like I said. It's used to store data. These data points can be anything: transactions, votes, product inventories. Like I said, there are multiple implementations of blockchains, multiple use cases, the most common being cryptocurrency transactions. And these can be public or private. Cryptocurrency uses the blockchain structure to publicly store its ledger of payments, transactions, and balances, and it has no intrinsic value. And I will talk a little bit more about cryptocurrency. All right, so just the basics on cryptocurrency. They are designed to allow for secure, decentralized transactions between users. This means, back to the decentralized part of the blockchain, does not rely on any government or bank, and it is open 24/7. Blockchain is always going, always chugging. And it is immutable because it is on the immutable blockchain. Meaning, if you mess up and you send crypto to the wrong address, it is gone. But it also means that if somebody pays you in crypto for something, they can't, if it was a credit card, they could call them and say, I didn't make that transaction, and charge you back. Well, with the blockchain, nope, it's immutable, can't go back, no take backs. It's gone once you send it. And there are several ways to acquire crypto, the most common being Coinbase transactions. These are the rewards that you receive for mining a new block. Staking, this would be if you already had some crypto. You can stake it kind of like in proof of stake, and then there's other decentralized apps out there that allow you to stake and earn rewards. And then airdrops, usually for participating in some kind of social media something, or signing up for a list. You can get crypto airdrop to your address. And then the most common way is purchasing. There are a lot of exchanges, both centralized and decentralized, that you can buy crypto on, either for other crypto or for fiat currencies. Just some theory on cryptocurrencies. Each user has a private key, which allows them to spend outputs or coins that they own, therefore making inputs. These inputs go to the next transaction if they get spent again. Each user has a public key, which allows them to receive their coins. And so the word address is also interchangeable with public key generally. This public key is derived from the private key, but the private key cannot be derived from the public key. It is a one-way derivation, if you will. This means that only the owner of the private key may spend the tokens associated with their public key, and only those who have the public key, the owner, may send coins to them. Inputs and outputs. Transactions are the basis of cryptocurrencies. They allow coins to be exchanged. Chris will talk about this a little bit more later on. Transactions are comprised of a set of inputs and outputs. Like we talked about, if you have coins sitting at your address, those are unspent outputs, and they get used as inputs in the transaction. These inputs describe where the coins come from, and obviously outputs where they go to, say your friend's public address or one of these staking contracts that I mentioned. Inputs must be signed by the owner of the coins with their private key. It's a transaction signature, like signing a check. If you didn't sign it, can't cash it. Since private keys cannot be derived from public keys, no one can forge your signature without obtaining your private key. Whenever you generate a private key on most platforms, they make you physically write it down, and then they prompt you to put it in again, and you can't paste it in. You either memorize it, write it down, both. You have to store it somewhere safe, because you will not get it again, and you need that private key to access your funds. All right, and here's Chris to talk about blockchain implementation.
All right, so we've talked about the blockchain implementation for the vast majority of the semester, so I chose a couple of elements to highlight. This is by no means comprehensive at all, because we have like 1,400 lines of code. Definitely couldn't do that in one presentation, so I just wanted to look at a couple key features. So first, let's look at the data structure of a block. Just going back to the basic slide you saw about the things a block might need to contain, we're going to need some elements of this that ensure immutability on the blockchain. So to start, we're going to want the index, which is the index of that particular block in the chain. So, the first block on the chain may be block 0, and then after that, they continue incrementing. So the next block would be block 1, then block 2, etc. The hash is going to be a hashed representation of all of the data in the block. That all it does is just take all of the data that represents a block and shove it through a one-way SHA-256 function. Previous hash is going to have the hash field of the previous block, and this is what ensures immutability. If you were to change, one block in the chain, then theoretically that means that you change that block's hash. The next block's previous hash would then have to change as well, and basically if you try to malform a single block in the blockchain, you consequently will malform every block after that block in the blockchain, and that makes it immutable. We need a timestamp here just to see when the block was made. We'll need a data field, and this can theoretically contain just about anything you want it to, that's serializable. In our case, this is going to hold the transactions. This is the cryptocurrency layers going to be implemented into that data field. We're going to need a difficulty field, and this is just some field you set to manage how much effort is necessary to mine a new block. And a nonce field exists just to modify the block hash. When you're trying to find a block that satisfies the difficulty, you'll need to modify the block to get a new hash each time, and that's what the nonce is for. You can just increment it to get a new hash for your block. So if we go on to the next slide, let's look at what it looks like to determine the block hash, for example. So the block hash function is just going to be taking all of the different fields of the function with the exception of a signature, which we can talk about later. And we're going to just take those, make a big string out of them, encode it as a bytes object, and pass it through an SHA-256 hash program or a function. And then we're going to get the a hex string representation at the end here, so that we have something a little bit easier to work with, something that makes sense to look at, and isn't a bunch of escaped characters. So if we go on to the next slide, we can see what mining a new block might look like. So first we have the generate next block generic function. What this does is this is kind of the root of all block generation in Blockchex. So first we're going to get the previous block. Then we're going to go ahead and make a basic block element given the information the user has passed, in this case the list of transactions. We'll need to add a little bit more in here, of course. This block will need to get solved, and in this bottom picture, you can see the solve block function. All it does is continue incrementing the knots until we find some hash that satisfies our difficulty. And then after that, we just go ahead and try and add our block to the chain. And this is what mining a block looks like. So if we're trying to add a new block to the chain, we're going to first see that the block is valid, because if it's not, then there's no point in trying to add it to the chain. If the block is not invalid, and it is in fact valid, then we're going to go ahead and process all of the transactions in that block so that our list of running unspent transaction outputs is current. And this means basically that you can check your balance reliably and make transactions reliably without forgetting, oh, I received this payment 6 weeks ago and I didn't remember it. That's a problem. It'll keep track of it for you here. So if we run our transactions through that and we find that there are no new unspent transactions, then the block is kind of useless and we just kind of get out of here. And if there are useful transactions in here, then we're going to head and put the block onto the blockchain. We're going to broadcast this block to our peers, and I'll touch more on that here in a few minutes. And then we're going to go ahead and actually update our script variable unspent tx outs to reflect the new unspent tx outs that we've just calculated. And then we're going to go ahead and return true just as a flag saying that we did in fact add the block that you tried to add. So let's take a quick look at the networking implementation. Again, there's no way I can touch on all of this, but I'd like to talk about a couple of the high-level features and maybe one or two functions in here. So the Blockchex daemon is going to use the Flask mini web server library in Python and its endpoints to do more than just communicate with the client, like you've seen it do previously. It's also going to be used to initiate data requests and use HTTP for transmission of data to and from other nodes. So you only have to set up a connection once. Once you've got it in your target list, then it'll just be maintained as long as your node is open, and you don't really have to mess with it past that. As far as initializing a connection goes, this is what the code looks like that accomplishes that. You would run this init target function with your target as a string, and you're just going to go ahead and add it to your list of active targets and try to get the latest block and do what you can with that information. So we just put our target on P in the active connection targets, query the latest block, and then after that, the connection is going to handle itself. Data will bounce back and forth as necessary. Validation happens on its own, etc. And we can look at a couple parts of that here in the next slide. So querying blocks from peers, if we pick up where we left off on the last slide, just querying the latest block is going to involve actually requesting the data from our peer at the Flask endpoint appropriate. And then we're going to have to deserialize the information because that's given to us as a bunch of JSON. And JSON, while quite lovely for sending and receiving information, is not great for processing it because that's not how programming languages work. So we're going to first make a dictionary out of this. And then after that, we're going to deserialize the block with a custom deserialization function. And I don't think we get much into serialization and deserialization in this final presentation because it's boring, tedious, and kind of self-explanatory. Comparing new blocks, I'm not going to talk through this whole function again like I have in the past, but this is an example of one of the large unwieldy functions that has to handle some corner cases here and there that make cryptocurrency a little bit unwieldy to learn, especially on the development side. But at its heart, what this function does is given a block from our peer, we're going to see all of the different possible cases that this block could align with our blockchain, seeing if it is, is this a new block and the rest of the chain, if the rest of their chain is the same as the rest of our chain, then we can just go ahead and plop their new block on here if it's valid. If it is behind us, if they've got block 7 and we've got block 532, then obviously we don't care about their block. and maybe they've got an entirely different chain, and we need to evaluate our chain to see if theirs is in fact just more mature than ours, and consolidate the network that way. And so this function will handle a lot of that functionality. So in conclusion, the networking, you get to see a brief peek at it through these past slides and a couple of the important functions. Connections will maintain themselves after you add a peer and will keep the nodes synchronized. The netcode is also the primary validation checkpoint for most of the code and most of the data. So you've seen the validation mentioned a couple times in this presentation already, and definitely in our previous weekly presentations, you've seen us talk about validation at length. That doesn't matter if you don't ever apply it, and where that is going to be most necessary is when you're checking your peers' data, because if you're checking your own data, whatever, you might want to malform it on purpose even. But if you're checking your peers, if you're getting information from your peers, you definitely can't blindly trust that, and you're going to have to validate it. And that's why the netcode implements validation. It's the primary validation checkpoint in the project. So if we look at the implementation of the actual cryptocurrency elements, the cryptocurrency layer, if you will, there's going to be a lot more of these large unwieldy functions. In fact, they're significantly worse than the networking or blockchain functions. And so again, we're just going to look at a few key functions in the cryptocurrency layer to kind of talk about what this looks like at a data level and what this looks like at an implementation level. So let's kind of talk about the big function, building a transaction. This is the ultimate goal of all of the cryptocurrency code and really all of the blockchain code as well. So this is going to rely on that a lot. So to start this function out, we're going to need to do is get our public key and private key sorted out here. And once we've got that, then we're going to go through our list of unspent transaction outputs and find all of the ones where the output address is the one that corresponds with our private key. Meaning basically we're looking for money that has been sent to us and has not been spent since then. So once we have that, we're going to actually choose a few specific TX outs, these outputs, transaction outputs, to fund our transaction. So if we need 15 coins and we have two different TX outs for 10 coins each, then we're going to need both of those, but we wouldn't need a third. And if we only provided one, then you would have insufficient funds and it would not be handled correctly. Or it would be handled correctly, but it would not let you make the transaction. No coins would be spent or sent. So if we go on to the next slide, we can take a look at the next few lines of this function. So the next thing we're going to do is map each of the items in our TX out list here and turn them into a TX in. Since these were previously transaction outputs that were sent to us and we're wanting to spend these, we're putting these coins into a new transaction. Thus, we need to make transaction inputs out of them, or TX ins for short. So for this, we're just going to go ahead and boilerplate constructor the TX ins out of the TX out data. If we go on to the next slide here, we can take a look at the last few lines of the transaction building function. So first, we're going to actually make the transaction object, and we're going to assign all of the information we have available to it to that object. We're going to generate a transaction ID on this transaction object, which now contains all of the relevant information except for the signatures on our TXNs. And once we have our transaction ID based on all of the information, and we have our TXNs and our TX outs and everything is assigned correctly, then finally we're going to sign each of the TXNs using the user's private key. And for that, we're just going to run our sign TXN function, which is also another validation checkpoint. And once we've got everything signed, then we're going to finally update the tx.txns field here to actually sign everything and make sure everything is working correctly. So after that, let's take a look at what processing transactions looks like. So we've seen what it looks like to build a transaction, but what if we receive transactions from our peers, or we have a block and we want to update whatever data may depend on the transactions? We're going to look at process transactions for that. So first, we're going to, for each of the transactions in our list of new transactions, we're going to make sure they're validated because we don't want to be applying changes based on invalid data. And once they are valid, we're going to return update unspent. An update unspent here is going to make sure to update the script variable in blockchain.py to make sure that we have the most accurate, most up-to-date version of all of the unspent transaction outs, meaning that when we try to spend our coins, we will be referencing an accurate set of data and not have to scan through the whole blockchain or whatever. So since we can't go into a lot of the serialization, deserialization stuff at length, I wanted to include just a little bit. This is what deserializing the network transmitted data for transactions looks like. So this is the data field of a block. Is going to yield some JSON. That JSON is very easily transformed into a dictionary, and with that dictionary, we can pass that into these functions. So the top level one is actually deserialized tx in the bottom, and from that, we're just going to try and loop through and add a deserialized version of each of our tx outs and tx ins. And once we have that, then we can form a transaction object, including these fields. And now we have taken a JSON dictionary that was passed to us over the internet and transformed it back into a transaction object in Python. And this lets us work with the information again. So there's a lot of serialization, deserialization stuff that shows up all over the code, and it's really ugly and boring to talk about, so we don't.
Yes, it is very not pretty. All right, so a little bit about the client. Client is the user's primary means of interacting with the blockchain. The client and the daemon run in parallel, and closing the client will also close the daemon with it. Here's just a look at what the client looks like. It is written in PySimple GUI. It is not the prettiest client, but it is functional and it does what it needs to do. I will just run through basically what it can do. Transaction screen. So if you hit send crypto, it will pop up and ask you for, hey, what address do you want to send it to and how much do you want to send it for? And then you submit that amount. And if it can happen, it happens. And if it can't, it can't, as outlined before. At the top, we have a menu. The wallet menu allows you to view your balance, and it allows you to load your public address into your clipboard, so you can paste it. Say your friend lost a bet and they owe you whatever, send them over your public address, and they can send you your funds. View in the view menu, we have a couple of functions that allow you to view individual blocks or the entire chain. And the blocks can be looked up by their height or by their hash. Just some basic ways to parse through the chain and find what you're looking for. The network menu allows you to view your current connections or initiate a new connection. If you initiate a new one, you're going to need their IP and the port that it's running on. Having a always running node and automatically populating these connections was a bit out of the scope of this project, but a more mature chain would surely do this on its own. And the help menu just takes you to our README page on our GitHub. And these are our sources. Thank you very much.
Yep, thank you guys.